All right, welcome to the deep dive. And, I have to say, we've got a really fascinating pile of articles and reports here today. So are you ready to really, plunge into this world and figure out what's driving the power industry forward, what the major shifts are in terms of technology, and just, the whole overall landscape?
Absolutely. Yeah, you've pulled together a really interesting mix. I mean, we've got articles on grid modernization, asset management, even how transformer installation works, plus, got a little political intrigue, the potential impact of a Trump reelection, right? And of course, everybody's favorite EV charging and how to actually make it work on a large scale.
Well, let's try to make sense of it all. I mean, our goal here is to sort of synthesize all this information, pull out the really key nuggets, and hopefully leave our listeners with a clear, a connected view of how this whole industry is evolving.
Sounds good to me. Let's dive in.
All right, so the first thing that really jumps out at me is this idea of a digital revolution in energy. And I think it's a lot deeper than just saying, oh, computers are important. Mm-hmm. It's about fundamentally changing how we think about generating, distributing, and even consuming electricity.
I think that's a great point. And it's about making the whole system more intelligent, right? I mean, we're talking about smart grids that use sensors and data platforms to monitor energy flows in real time.
Yeah.
We can optimize how that energy is being distributed, even automatically reroute power when there's a problem.
It's almost like, the grid is developing a brain of its own, and it's able to respond dynamically to changing conditions, outages, all sorts of things.
Exactly. And it's not just about making the existing grid smarter either. Digitalization is absolutely essential if we want to bring more renewable energy sources online.
Oh, for sure, because solar and wind, they can be a bit unpredictable, right? And that presents a real challenge when you're trying to manage a stable power grid. But digital tools are becoming crucial for things like, more accurate weather forecasting, better balancing of supply and demand, and figuring out how to manage energy storage effectively.
And if we think about this from the consumer's point of view, digitalization brings a lot more transparency to the table.
Yeah.
Imagine digital platforms that give you really granular data about your energy usage, so you have much greater control and can even participate in programs that incentivize you to, shift your energy use to off-peak times.
Right. So it empowers people, at least in theory. But I'm also seeing a lot of challenges here. The articles talk about the massive investments we need to make to upgrade a lot of our infrastructure, which is, pretty outdated in a lot of cases. And then there's the whole issue of cybersecurity, which is a constantly evolving threat.
Yeah. And then you throw in the world of regulations and policies, which can be complex and sometimes really slow moving. Try to navigate that can be a real headache.
For sure. Plus, making sure all these different digital systems and technologies can actually talk to each other, work together seamlessly, that's huge. We need standards, and things need to be interoperable if we want this to work on a large scale.
And let's not forget about the people involved, right? We need a workforce that can design, operate, and maintain these increasingly sophisticated digital systems. So, addressing the skill gap through education and training, that's really important too.
It seems like making this digital revolution happen is going to require a lot of collaboration. Governments, utilities, tech companies, even consumers, everyone needs to be on board.
Couldn't agree more. It's a huge collective effort.
All right, well, let's shift gears a little bit and talk about how modern monitoring technology is changing how we think about managing renewable energy.
Yeah, and I think the big takeaway here is just the sheer increase in the amount of renewable energy being generated. I mean, it's growing rapidly. And that introduces a whole new set of challenges for keeping the grid running smoothly. Wind and solar farms, they require different maintenance approaches compared to traditional power plants.
And the economics of energy are changing so dramatically. That Deloitte report you shared, it points out that in parts of the U.S., it's actually cheaper to build brand new solar or wind farms than it is to keep existing coal-fired power plants operating. It's like a huge shift.
Yeah, the cost of renewables has come down so much that it's completely changed the equation. But on the other hand, actually managing these renewable energy installations, it can be really challenging. I mean, think about inspecting hundreds of wind turbines spread out over a huge area, or, monitoring those vast solar arrays. Doing that manually is incredibly inefficient.
And that's where this concept of continuous automated monitoring comes in. Using things like thermal and visual sensors, we can remotely monitor critical equipment at wind farms, substations, transformer sites, even down to the inverter level.
It's like having a virtual team of inspectors that are always on duty, 24/7. And the benefits are huge. You can identify potential problems much earlier, you can dispatch maintenance crews more efficiently, and you ultimately make the grid more reliable by preventing those big, costly outages.
The articles also talk about some more specialized monitoring needs. For example, HVDC technology, high voltage direct current, is being used more and more for transmitting large amounts of power over long distances. And for those HVDC converter halls, infrared monitoring is becoming a crucial tool.
Oh, absolutely. Especially because those environments can be hazardous for personnel, so having a remote monitoring solution is essential for safety and for making sure the equipment is operating reliably.
Another key area is the rise of utility-scale battery energy storage systems, or BSS for short. As we add more renewable energy, these batteries are becoming essential for balancing the fluctuations in supply and demand. But we're seeing a huge increase in battery deployments, and monitoring their condition continuously is critical, especially from a safety perspective.
Yeah, battery technology is advancing rapidly, but large-scale battery systems do present some potential hazards, so having robust monitoring in place is non-negotiable.
Okay, so I keep seeing this term Energy 4.0 pop up. Can you give us a little more insight into what that actually means?
Sure. Think of it as this convergence of a bunch of really powerful digital technologies. We're talking about the Industrial Internet of Things, or IoT, which is basically connecting all sorts of industrial equipment to the internet. Then you've got cloud computing for storing and crunching massive amounts of data, advanced analytics to make sense of that data, and artificial intelligence, or AI, which includes machine learning, to identify patterns and make predictions.
So instead of sending a technician out to check a piece of equipment on a fixed schedule, we can use data to tell us when maintenance is actually needed and potentially even prevent problems before they happen.
Exactly. And moving to cloud-based solutions for accessing and analyzing all this sensor data, it makes everything so much more efficient and scalable compared to the old way of doing things with, on-site IT infrastructure. It's a big step towards creating a truly resilient and future-proof grid.
Okay, well, let's move on to this idea of how technology is making asset management more accessible. It sounds like the traditional ways of managing our energy infrastructure are facing some pretty serious challenges.
That's definitely true. I mean, we're dealing with a generation of really experienced professionals who are starting to retire, taking a ton of knowledge with them. And at the same time, our energy systems are becoming so much more complex with all these new technologies being integrated. So yeah, it's a tough situation for managing those critical assets effectively.
The sources keep talking about democratizing asset management technology. So what does that actually look like in practice?
Well, it's about making sure that sophisticated tools and insights are available to a much wider range of people within an organization, not just a small group of highly trained experts. It's about empowering more people with the information they need to make good decisions about our energy infrastructure.
And what's interesting is that it doesn't always have to involve super advanced, complex technologies. Some of the articles highlight really practical, almost low-tech innovations that are having a big impact.
Yeah, for sure. Like, take those thermochromic overtemperature indicators, for example. It's basically a little sticker that changes color if a piece of equipment gets too hot.
Yeah.
Anyone can see that and understand that there's a problem that needs attention. Super simple, but really effective.
Right. It's a great example of how a low-tech solution can be a really valuable safety measure. And then on the more high-tech side, you've got things like using NFC tags on equipment. So a technician can just scan a tag with their phone and instantly get access to, the maintenance history, specs, all sorts of critical information about that specific asset.
And then, of course, you've got AI. AI is changing everything. It can analyze those huge data sets we're collecting, find patterns that humans might miss, and prioritize maintenance actions based on urgency and potential impact. We're even starting to see generative AI being used to, go beyond just identifying a problem and actually generate detailed plans for how to fix it.
So that could really streamline things and make maintenance teams so much more efficient. And I imagine AI also has a role to play in, broader sustainability efforts. I mean, optimizing energy use, predicting equipment failures that could lead to environmental hazards, things like that.
Oh, absolutely. AI has the potential to make a big difference in all those areas. But, as with any new technology, getting it widely adopted is not always easy. There's often a certain amount of distrust. And to build confidence, you have to prove that these AI-powered systems are transparent, that their recommendations are reliable, and that they actually deliver real-world benefits.
And it seems like data overload is another challenge. I mean, it's one thing to collect tons of data, but you need the systems and platforms that can actually make sense of it all, synthesize it, and present it in a way that leads to actionable insights.
For sure. Just having data isn't enough. You have to know what to do with it. And as with any major organizational change, having buy-in from leadership from the top down is absolutely crucial if you want to drive the adoption of these technologies.
In one of the articles, we had the chance to hear from Seamus Allen at Dynamic Ratings, and he had some really interesting insights on these challenges and opportunities in asset management.
I thought his comments about the knowledge gap were really spot on. As those experienced professionals retire, you have a lot of younger engineers coming in who haven't necessarily had the same level of hands-on experience with the equipment they're now in charge of managing. It's a real concern.
And that's where Dynamic Ratings comes in. They focus on providing online monitoring of asset health and then interpreting that data to provide utilities and grid operators with actionable intelligence. It's a move away from those traditional manual inspections and more towards a data-driven, proactive approach.
He also made a great point about data overload.
Yeah.
It's not enough to just collect mountains of data. You have to be able to filter it, analyze it, and present it in a way that's easy for those younger engineers to understand and use. They need to see the insights, not just a bunch of numbers.
Right. And he talked about the strain on the grid, too, which is a really big deal. With all the inverter-based generation coming from renewables and the growing demand from things like EVs, the grid is really being pushed to its limits. He mentioned a statistic that, only 10% of circuits in the U.S. might be able to handle the projected loads in the future. That's a pretty stark number.
It definitely highlights the urgency of investing in grid modernization.
Mm-hmm.
And he made an interesting comparison to the early days of electrification in the early 1900s. There was this huge push to build out the grid, but this time around, we don't have the same kind of workforce available. So relying on data, intelligent asset management, automation, all of that is going to be crucial.
He's a big advocate for industry collaboration, too. He talked about organizations like CIGOR, where engineers and experts from all over the world come together to share their challenges and solutions. And it's cool that Dynamic Ratings actually incorporates best practices and recommendations from these groups into their systems.
And his point about encouraging people to get involved in those kinds of organizations to share their knowledge, that really resonated with me. I mean, the more we collaborate and share what we're learning, the faster we can innovate and solve these big challenges facing the power industry.
All right, well, on that note, let's talk about some of the specific technologies that are being developed and deployed for grid modernization. It's pretty clear that this industry is going through a period of really rapid evolution.
It is, and I think it's being driven by a whole bunch of factors all happening at the same time.
Mm-hmm.
The large-scale integration of renewables, the growth of distributed energy resources, more EVs, the demands from data centers, rising customer expectations, climate change, and the way our transmission and distribution systems are becoming more interconnected. It's a lot to deal with.
So modernizing our distribution systems, making them capable of real-time operation, advanced planning, being able to predict problems before they happen, all of that seems absolutely critical. And the sources list a whole bunch of technologies that are being deployed to do that.
Yeah, we're seeing things like advanced metering infrastructure, or AMI, digital relays, distribution automation systems, sophisticated telecommunications infrastructure, and advanced distribution management systems. It's a pretty long list.
And one technology that really caught my eye is soft open points, or SOPs. They're essentially a way to apply flexible AC transmission systems, or FETS, to the distribution network. So using power electronics to give us much more control over things like voltage, current, and how power flows in our distribution feeders.
Right, and the idea is that you install these SOPs at points in the network that are normally open, and that allows for more flexible, dynamic control of the power flow. So it's almost like creating a closed-loop system.
So what are the big advantages of doing that? What problems does it solve?
Well, it gives you really precise control over how power is moving between different parts of the grid. So you can do things like balance the load between two adjacent feeders. You can avoid or delay having to make expensive upgrades to increase capacity. And you can improve the overall reliability and resilience of the system. Plus, it allows you to integrate more distributed renewable energy sources and can even reduce energy losses.
So instead of operating in that traditional radial fashion where power flows in one direction, we can create a more interconnected and adaptable system. And that example in one of the articles showing those two feeders, it really illustrates how an SOP can dynamically balance the demands between them without being limited by a static, normally open point.
Exactly. And there are real-world projects that demonstrate this. The UK Power Network's Active Response Project is a great example. Now, closed-loop operation with SOPs, it's a really promising approach, but it does require more sophisticated protection systems, more robust equipment, and it changes how we think about operating the grid. So there are some adjustments that need to be made.
Okay, well, the discussion then moves on to this idea of leadership and collaboration, and it seems like technology alone isn't enough to solve all the problems we're facing.
Definitely not. The sources really emphasize the need for strong leadership from governments, setting clear policies and long-term goals. Things like ambitious net zero targets, carbon pricing mechanisms, and consistent incentives for businesses to invest in clean energy technologies. There's a feeling that past government actions have been too fragmented, not really impactful enough to drive the kind of change we need.
And when you think about the scale of the energy transition, it's mind-blowing. We're talking about electrifying transportation, heating, and industry. That requires a massive increase in clean electricity generation and a total overhaul of our grid infrastructure. It seems like the current level of investment, which often focuses on pilot projects and specific technologies like EVs and batteries, it's just not going to be enough.
We need a much more comprehensive and strategic approach. That means big upgrades to the grid itself, developing long-duration energy storage solutions, and making sure our supply chains for critical components are resilient and, ideally, more domestic. And collaboration across the private sector is essential, from the companies that supply the raw materials all the way to the manufacturers.
And given how interconnected the North American grid is, closer collaboration between the U.S. and Canada is going to be really important.
Absolutely. We're all in this together.
The articles also mention the need for more focused industry events, and they highlight this Power Transmission and Distribution Technology Expo that's happening in Germany in 2025. It sounds like it's designed to be a showcase for, the architecture and the technologies that are going to underpin these next generation grids.
Yeah, I think it's a great idea. It gives professionals in the industry a chance to see what's cutting edge, what's new, and to really foster those collaborations that are so essential.
We also got a glimpse inside DuPont's European Technical Center in Switzerland, and they're doing some fascinating work on advanced insulation systems for transformers and motors. They have this global network of technical centers, and it's clear that collaboration is a big part of their R&D process.
And they have incredible testing facilities. I
Yeah.
mean, they can simulate all sorts of real-world stresses on these insulation materials. Like, they have this machine that can generate intense electrical pulses that are similar to what you see with modern silicon carbide components. And they can do extreme thermal and mechanical stress tests as well. So they really put these materials through their paces.
What I found interesting is their focus on consistency. They want to make sure their testing methods and the materials they use are highly standardized, and they actively participate in industry groups like CIGRE. Plus, they're innovating in transformer design, specifically for renewable energy applications. They're using their Nomex insulation to create transformers that are smaller, more efficient, and lighter, which is ideal for things like wind turbines.
Yeah, and using Nomex allows for some really clever design optimizations. You can reduce the need for those big cooling ducts, which saves space and improves the overall efficiency of the transformer.
And their commitment to collaboration extends throughout the entire life cycle of their products. They even do testing on materials at the end of their life to help inform future development.
Yeah, it's a really holistic approach.
Okay, well, let's dive into this discussion about dynamic thermal and moisture distribution inside transformers. It sounds like understanding how heat and moisture behave within those critical pieces of equipment is really important for their reliability and lifespan.
It's essential. The insulation system inside a transformer is really the key to its longevity. So, understanding how heat is generated and dissipated and how moisture moves between the liquid and solid insulation components, that's crucial. And this whole moisture migration process, it's really dependent on temperature and the specific properties of the materials being used.
And if there's too much moisture, it can really speed up the aging process of the insulation and weaken it both electrically and mechanically. But measuring the moisture content inside an operating transformer, that seems like a tricky thing to do.
It is, and the articles talk about the two main sources of moisture. It can be generated internally as the solid insulation ages and breaks down, or it can get in from the outside environment over time. And what's interesting is that just measuring the water content in parts per million in the insulating liquid, that doesn't always give you a complete picture of the moisture situation, because different insulating liquids have different capacities to hold moisture.
That makes sense. They give an example comparing synthetic ester, natural ester, and mineral oil, all at the same temperature and with the same water content in parts per million. But their saturation levels are different.
Exactly. So knowing the parts per million of water in the oil doesn't tell the whole story. And the temperature differences inside a transformer, especially the presence of hot spots during periods of high load, that can really affect how much moisture the insulation can hold. So you have to take those temperature gradients into account.
And they talk about this concept of the relative saturation ratio, or RSR, and how it relates to those temperature variations. And using these equilibrium moisture isotherm curves, you can actually estimate the water content in the solid paper insulation based on measurements from the liquid.
It's a complex process, but it's essential for getting a really accurate picture of the health of the insulation system.
One of the articles features an interview with Gordon Adamanchuk from Microtool and Machine Ltd., a Canadian company that specializes in building coil winding machines and canal cutting equipment for transformers. His background in product testing and development gives him a really unique perspective on the manufacturing side of things.
Yeah, and I thought it was interesting that he emphasized MTM's focus on cost-effective automation solutions. They're really trying to help transformer manufacturers increase their productivity, standardize their processes, and address the labor shortages that are affecting so many industries. And with the huge demand for transformers, driven by things like grid modernization and data centers, that makes perfect sense.
He talked about the challenge of moving from manual to automated winding processes, especially with those labor shortages. So MTM designs their machines with really intuitive interfaces like touchscreens to make it easier for operators to learn and use them. And they're automating a lot of those really critical steps like wire tensioning to improve consistency and quality and minimize errors.
And they have a really flexible approach to machine deployment, too. Their machines can handle a wide range of transformer sizes and types, and they can be reconfigured pretty easily to adapt to changing production needs.
Right, so you could have a single machine that can switch between winding multiple small coils in a single large coil, or they have combination machines that can do both low voltage and high voltage windings. And he stressed the importance of customer support, making sure their customers are successful throughout the entire life cycle of the equipment.
Okay, well, let's move on to this discussion about the undamped nature of the modern power distribution system. It sounds a little ominous. Can you break down what that actually means?
Yeah, well, if you think about how power distribution evolved, it started with DC, primarily for lighting, and then transitioned to AC, mainly to power industrial equipment. And for a long time, the types of electrical loads connected to the grid were pretty simple. But now, with everything becoming electrified and with all the power electronics and things like LEDs and variable frequency drives, the load profiles have become way more complex.
And these so-called nonlinear loads, they don't just draw current smoothly. They actually inject harmonic currents back into the AC system, which can cause problems. And on top of that, you have the rapid shift towards renewable energy sources, which also rely on power electronics, specifically inverters, to connect to the grid.
And all those inverters, they're also introducing harmonic currents into the system. Okay,
Yeah.
so every AC power system has capacitance and inductance, right? And those things can interact and create a phenomenon called resonance.
Exactly. And every AC system has a natural resonant frequency. Historically, with mostly linear loads and conventional generation, the chances of actually exciting that resonance were pretty slim. But the modern grid, with all those nonlinear loads and inverter-based generation, it's regularly generating harmonic frequencies that can coincide with the system's resonance, and that leads to these elevated harmonic current and voltage levels.
So it's like we're pushing the grid at its resonant frequency more often, and that can cause problems. What kind of problems?
Well, you can see things like increased stress on equipment, overheating, interference with sensitive electronics, and in some cases, it can even damage the grid itself. The articles recommend deploying dedicated power quality analyzers throughout the system to monitor these harmonic levels. And they need to be sophisticated analyzers that can measure high-frequency harmonics and really fast transient events, not just rely on traditional protection relays or voltage regulators. And they also suggest that instead of just adding more capacitors to the system, which can actually worsen the problem in some cases, we might need to think about using filters to dampen the system's response and avoid those resonance issues altogether.
All right, so the last topic we need to cover is, it's a bit politically charged. It's about the potential impact of a Trump re-election on the energy transition. And I have to say there's definitely a sense of uncertainty in the industry about what that might mean.
Yeah, there's definitely some anxiety out there. I mean, President Trump has expressed skepticism about renewable energy in the past, and his administration rolled back some environmental regulations, and his statements about potentially repealing or weakening incentives for renewables like those in the Inflation Reduction Act and putting a stop to offshore wind projects, That's definitely causing some concern.
But the articles also point out that a complete reversal of the IRA incentives is probably unlikely. The renewable energy industry has grown significantly, it has a lot of support at the state level, and there are now a lot of investments in renewable projects, even in districts that are represented by Republicans.
So while we might see continued growth in renewables, the pace could be affected, and certain sectors like offshore wind might face more challenges. The market for power grid equipment is still projected to grow, driven by the need for more electricity and the integration of renewables. But we could see shifts in sourcing, maybe a move towards more domestic manufacturing due to things like protectionist trade policies.
And what about the EV market? That seems like it could be particularly vulnerable to policy changes.
Yeah, if those federal tax incentives for EV purchases were to be revoked, that could definitely slow down adoption rates. And increase tariffs on imports from China, which is a major player in the EV battery supply chain, that could push up costs. Plus, there's uncertainty around the USMCA trade agreement and whether that might be renegotiated. All of that adds a layer of complexity. However, there's also been a lot of investment in building EV manufacturing facilities in the U.S., so there's definitely some momentum that's likely to continue.
So the takeaway seems to be that a Trump presidency could create some headwinds for the energy transition, but the long-term trends are still pointing in the right direction. And the companies operating in this space are going to have to be adaptable and be prepared to navigate those potential policy shifts.
Absolutely. Flexibility and resilience are going to be key.
Okay, our final topic is about how Edge AI is being used to optimize the placement and operation of EV charging infrastructure. And with the rapid growth of EVs, especially in Europe, efficiently managing all those charging stations is becoming a big deal.
It is. And it sounds like grid operators are turning to Edge AI solutions to help them manage those charging stations more effectively and to lower their operating costs. It's all about making the most of those charging assets.
So can you explain what Edge AI actually involves in this context?
Sure. It's basically about processing data locally at the charging station level, using advanced monitoring systems and AI models that can make predictions and decisions in real time. So instead of sending all the data back to a central server for processing, you're doing it right there at the edge of the network, which allows for much faster response times. And you're using AI to optimize things like charging rates and to make sure the charging station is operating as efficiently as possible.
And they're integrating this Edge AI with the existing grid infrastructure, using things like smart edge nodes and smart energy meters to make sure everything is working together smoothly and to optimize power distribution.
Exactly. And AI is also being used to help figure out the best locations for new charging stations.
Right.
I mean, you want to put them where they're going to be most useful and where they're going to have the least impact on the grid. So they're using AI to analyze things like traffic patterns, population density, existing grid capacity, the layout of the local distribution network, and even things like whether there are amenities nearby, like shops and restaurants that would make it more convenient for people to charge their cars.
And it sounds like they're using some pretty sophisticated tools to do that. I mean, they're using things like Voronoi diagrams and k-means clustering, which are concepts from geometry and data science, to figure out the optimal placement. And those examples from Oxfordshire County Council and the Royal Military College of Canada really show how these techniques are being applied in the real world.
Yeah, it's really cool to see how these advanced analytical tools are being used to solve practical problems.
And once the charging stations are deployed, they're using smart control systems and various load management techniques to minimize the impact on the grid. Things like load balancing, where you shift charging to off-peak times, and dynamic pricing, where the cost of charging fluctuates based on demand.
Right. And so what kind of results are they seeing from using Edge AI in this way?
Well, they're seeing significant improvements in a bunch of areas. They're optimizing predictive maintenance for the charging stations, which means fewer breakdowns and lower maintenance costs. They're reducing the cost of providing customer support, and they're minimizing those expensive callouts for repairs. And from a business perspective, there's a clear return on investment. The charging fees themselves generate revenue, plus there's potential for partnerships and advertising at the charging locations. And users might get benefits like priority charging.
And perhaps most importantly, Edge AI is helping to maintain grid stability as more and more EVs come online.
Exactly. It's constantly monitoring the charging demand and the available grid capacity, and it can adjust charging rates dynamically and even use battery storage at the charging stations to balance the load and prevent those big spikes in demand that could overload the grid. And it leads to operational efficiencies as well through AI-powered predictive maintenance, which allows for remote troubleshooting, automated scheduling of maintenance tasks, less downtime, and lower costs.
It's really a game changer for deploying and managing EV charging infrastructure. It offers all sorts of benefits in terms of performance, cost savings, and efficiency, all of which are going to be crucial as the EV market continues to grow.
All right, so to wrap things up, we've covered a lot of ground today. We've seen how digitalization is really a foundational element for creating a modern energy system. We've talked about the crucial role of advanced monitoring technologies in managing those increasingly important renewable energy resources, and how technology is making it possible to manage all those critical assets more effectively and make that knowledge accessible to a wider range of people. We explored the challenges and opportunities in modernizing our grids using innovative solutions like soft open points. We considered how potential policy shifts could impact the energy transition, and we examined how edge AI is revolutionizing the world of EV charging infrastructure.
And as we've seen, all these trends are really interconnected, each one influencing and shaping the future of the power industry.
So here's a final thought for you to consider. Given the incredible speed of technological advancement and the constantly changing energy landscape, what area do you think holds the most potential for disruption and innovation in the next decade? And maybe even more importantly, what are the key questions we should be asking right now about how these technologies are being developed and deployed?
That's a really interesting question, and it's something we all need to be thinking about as this vital industry continues to transform.
Well, thank you for joining us for this deep dive into the forces shaping the modern power industry. We hope you found it informative and insightful. And until next time, keep exploring the fascinating world of energy.